Okay, so let's read off the Insights article perspectives from the same issue of Science on 10th January. As we said, here is a classic picture of concrete being poured. We know how this all happens. Building materials such as cement and concrete aggregates could be used to capture and store a large amount of atmospheric CO2, as we just said with the estimates. Built to remove carbon, building materials could facilitate long-term removal of atmospheric dioxide. It's kind of a perspective on that article. According to current climate science, global temperatures will continue to rise until net carbon dioxide emissions reach zero. That is when the amount of CO2 added to the atmosphere is balanced by the amount removed, obviously background material, which we have discussed already elsewhere. Given current projected emissions, 2 billion to 15 billion tons of CO2 may need to be removed from the atmosphere annually to meet the goal of the 2015 Paris Agreement to limit the global warming to below 2 degrees C and preferably to 1.5 degrees C above the pre-industrial temperatures. However, a sustainable technique to capture and permanently store such large amounts of CO2 from the atmosphere is yet to be developed. On page 176 of this issue, the article we looked at reports that replacing traditional building materials with CO2 storing alternatives could sequester carbon at the billion-ton level, which is kind of the watermark we want to hit to be realistically relying on carbon capture as a part of the solution for meeting global warming targets. Considering the large human demands for infrastructure and buildings and their long lifetimes, the proposed strategy could provide feasible long-term CO2 removal. Building materials such as asphalt, wood, stone, steel, and concrete are foundational to human civilization and have large global demands which are predictable. For example, 30 gigatons of concrete are used each year in the world. 30 gigatons. Some of these materials are also major contributors to CO2 emissions. The production of cement, which constitutes up to 15% of concrete mass, requires heating at 1450 degrees centigrade and generates a substantial amount of greenhouse gas emissions from the limestone calcination process, the separation of limestone into calcium dioxide and CO2 by use of heat. Cement production accounts for 7.8% of the CO2 and 5.1% of the greenhouse gas emissions. So, what if building materials, especially concrete, asphalt, and bricks, could be made in a way that captures and stores atmospheric CO2? We already read the details, but it's fun to read it after the original article and say, hey, we already know this. So the paper we read performed quantitative analysis of CO2 storage capacities of key building materials based on 2016 global consumption of each material. The authors assumed that all carbon in the materials was from the atmosphere and that its storage was permanent. The combined CO2 storage potential of building materials was estimated to be 16.6 gigatons with some uncertainty of around 2.3 gigaton or so, which corresponds to 50% of the total CO2 emissions in 2021. Although several different building materials were analyzed for their CO2 storage potential, asphalt aggregates, bricks, cement, and concrete aggregates demonstrated the largest storage potentials because of their sheer demands. Van Rooyen et al., the paper we read, show that replacing just traditional cement and concrete aggregates with CO2 storing materials could remove 13.1 gigaton of atmospheric CO2 annually. Pretty impressive, right? So we won't read all the details here because we already did that. Key challenge, of course, to creating building materials for CO2 storage is the quantity of available feedstock resources, so carbonatable materials, magnesium, iron, and calcium oxides, and olivine family of materials such as magnesium, iron, and calcium silicates can react with atmospheric CO2 to form carbonates such as magnesium, iron, and calcium carbonates. So that's the figure we'll look at here in a minute. So given that olivines may not be available everywhere, limestones, which is a common precursor of cement production, could be used additionally as an alternative. However, Limestone calcination produces substantial amount of CO2 gas, as we just saw. The LILAC, Low Emission Intensity Lime and Cement project, was initiated to develop an inexpensive way to capture the CO2 produced during limestone calcination by injecting CO2 byproduct from the calcination process into the ground for storage. So there are other similar attempts. To successfully implement the use of CO2 storing building materials, new financial incentives and regulations at the national and regional levels will be necessary to trigger market uptake of building materials-based sequestration. So obviously we said traditional materials are winning the competition in terms of economic affordability and rapid access and supply chains, reliable supply chains and so on. So you need to create incentives for these alternative materials to be taken up much more rapidly so that the production can also be scaled up. Additionally, to ensure that these activities permanently remove atmospheric CO2, a robust monitoring, reporting and verification system is needed for tracking greenhouse gas emissions across the supply chain, which would then be confirmed by a credible third party. So some logistics issues of saying that we're putting away carbon and really it's staying there. So MRV, or monitoring, reporting and verification, is always critical for any of these claims to be validated. There are industries that may attempt to purchase carbon offset credits from building material producers to counterbalance their fossil fuel combustion emissions and claim to cut their CO2 emissions to net zero. This could bring unexpected outcomes if monitoring, reporting and verification effort is inadequate and projected reduction in CO2 emissions is not met. So every time you say we can hide CO2 somewhere, there is somebody saying, oh, can I pay for my offset so that I can continue to emit and you hide the carbon for me, which means you are really not reducing emissions as fast as you should, because if everybody reduces emissions, then additional sequestration can only get us faster to the global, or more reliably to global warming targets. So this has happened in the cases of certain ozone depleting chemicals and forestry and land use carbon offsets, in which the lack of adequate monitoring and accounting efforts led to emissions reductions being less than estimated. Industries are profit motivated, corporations, etc. Transparency is important, but also they are not a person, they are not owned by anybody. They could be publicly traded, and we may all be owners because my retirement savings may be invested in some such company without my knowledge, because these are aggregated investments. I don't manage it myself and so on. So we are all in this together. Nonetheless, with proper incentivization and monitoring, the use of CO2 storing building materials could provide a viable method for billion-ton scale CO2 removal at a reasonable cost. Okay, so this is some additional information here. CaCO3, calcium carbonate, magnesium carbonate, magnesium silicate or phosphorite are all being shown here for transformation. So carbon capture by building materials, carbonatable concrete aggregates such as calcium oxide, magnesium oxide and silica can absorb and react with the atmospheric carbon dioxide to form carbonate compounds. These materials are separated from natural resources by heating or acid leaching. This process could be used to remove a large amount of CO2 from the air and provide long-term storage. So here is limestone going in to break it into calcium oxide, and then the emitted CO2 can be captured and stored. And you can also use low emissions intensity lime and cement, LILAC, radiating heat. These are the processes that are standard for Portland cement, for example, clinker production, CAO. And then cement mortar. So building materials are here, maximizing atmospheric CO2 removal by masonry, cements and concrete aggregates with these intermediate processes where carbonatable minerals react with CO2 and are used as aggregates in concrete. So atmospheric CO2 is taken up, carbonation of aggregates happens, so magnesium, calcium carbonates are put into these materials. Here you have also the olivine family minerals, Mg2Si4. electric heating or acid leaching to separate carbonatable materials, MgO and SiO2, silicate magnesium oxide, and also bring them into maximizing atmospheric CO2 removal by masonry, cements, and concrete aggregates. All very nice in terms of theory, implementation, and tracking scope 1, 2, 3, all emissions, and monitoring and verification of additional carbon sequestration and the permanence, how long they stay there, are all critical. But exciting direction, of course. We take whatever we can, and the potentials are obviously there to what did I do? Did I close it? Okay, so I don't know, I'm doing something else as I'm talking, but this is just a brief summary of the main paper we read. But if you're lazy to listen to the 20-minute podcast of the paper, you can listen to this summary of 11 minutes and be done with it. Okay, see you.